Hello everyone. Today I'll be talking about what I learned this year in quarter 3 in Mr. Freddy's math class. In the entire year, oh sorry, not year. In the entire quarter, we learned by doing 6 big projects. So I'll be explaining what we learned in each of these big projects one by one. Let's start with big project 1. The first big project was all about simplifying equations and learning about the commutative and associative property of multiplication and addition. So let's get started. Let's first start off with simplifying an equation. So here we go. Okay, white. Let's start with this equation. We have x very neat, plus 3 and then 3x minus 8 plus minus 9 times 3x plus, there we go. This is indeed. So then let's get started. So let's decrease the brush size. To solve this, we first have to find out the groups that are very similar to each other. So let's find out a group using a different color. So one group would be x plus 3, right? And the rest would be 3x minus 8 minus 9, and then we turn it back to red because it's similar, it's equal to each other, x plus 3. So then what we have to do here is group the x plus 3 together, and when we do that, it will turn into this x plus 3, and then the remaining of the last group will be this 3x plus 8. So we can just take 3x plus 8, 3x minus 8, and since we have minus 9 there too, we can remove the brackets and make it minus 9. And then from there we can just simplify it. Let me just turn it to like green. Okay, so we can just simplify it into this answer, x plus 3, and then it's going to be 3x minus 9 minus 8 minus 9, which is negative 17. So this is basically how we learn to rewrite expressions so that it's easier to simplify. Okay. So the next thing that we learned from our first big project was the commutative and associative property of multiplication. So let's get started. So the commutative property, let's just set it as C because it's hard to write, states that it says there that the order of the terms that are multiplied together can be changed if it's multiplied or added. So for example, we have here 3x, right, times y, right, in brackets, multiplied by 4, for example. So then we can just turn it around, right, and put it there in the beginning. So it can become 4 times 3x times y. Now this one, it just changes the where 4 is positioned, and yet it will still stay the same answer when you simplify it later on. So then we can also do this with addition. Let me just erase this real quick. Okay, addition, where we have here, for example, 4x plus y and 8, for example, and we can just move 8 to the beginning and it will stay the same, right? 8, so 8 plus 4x plus y. There we go. So it still stays the same. That's the commutative property, as you can see here. Now then, moving on, we have the associative property. So the associative property states, let me write here an A. It states here that the grouping of the terms can be changed and the answer will still stay the same. So for example, our last example here, 3x plus y, sorry, times y, sorry, let me erase that, times it with y, and then we multiply it with 4, right? This means that the grouping, if they're all multiplied, right, if you can see here, they're all multiplied, we can group it to become 3x times y times 4, and the answer of all of this will still stay the same. And we can move the groupings to be y times 3x, right, and multiplied by 4, yeah, and so on and so forth. And yeah, the same thing goes for addition. If you let me just erase this. If you take 4x plus bracket 3y plus 8, then you can just move it to become 4x plus 3y plus 8, and the exact same answer will be given. So basically this was the associative property and the commutative property. So in our second big project, we learned how to multiply, add, and subtract two different equations with each other. So for example, here we have here g of x, right, which is equals to, let's just make that a different color, 4x squared plus 8x minus 9. Okay, and then we have here, make it back to white, sorry, f of x equals to a linear, so that's easy, green, make that green. Oh, okay, made it wrong there. Equals to 5x plus 10. So I'm just making this up as we go. And then, for example, there comes up a rule where it asks you to make it g of x, right, plus f of x. Sorry, that's f. Sorry, now let me erase that. F of x. Now then we can just put this, bring it down here, make it 5x plus 10. No, I should make that color coded. Yeah, it's fine. And 4x squared. Oh, sorry. Let's just remove this for more space. And then we have here plus 4x squared plus 8x minus 9 in brackets. So then we can just add this, and we scroll down to become 4x squared plus 5x plus 8x minus 9 plus 10. And we can just add these together and these together, and it becomes 4x squared plus 13x minus 9 plus 10 is equals to 1. So yeah, this is our answer from all of that, right? So yeah, this is the first part that we learned. Also, we can do this with subtraction. Let me just erase this then. Make it bigger. There we go. Right, and there we go. So we can also make it just g of x times f of x. And I keep making the same mistakes. F of x. So we can just put this and multiply them together. Now then, here comes the rule that we learned from our previous years in Mr. Freddy's class. Whenever multiplying, you have to multiply all the terms with each other like this. So this one has to multiply with this one has to multiply with this one has to multiply with this one, this, so on and so forth. It gets messy. So then what we can do here is we can just group them, make them different colors. So 4x squared times 5x is 20 x to the power of 3. Okay, and then the next part is 4x squared plus 10. Let's make that a different color, red. Okay, plus, yeah, it's plus, so it's 40x squared. Okay, the next part is 8x times 5x, so that's 40x squared. Oops, 40. There we go, 40. Sorry, that's a 40 there. And as you can see, they're one group, right? And then the next one is 8x times 10. Let's make that a different color. 8x times 10. So that's 80x. And then have that be negative 9 times 5x. It's the same, so negative 9. Oh, sorry, that should be minus negative 9 times 5x, which is negative 45x. And then have negative 9 multiply with 10. As you can see, this is one group. Just solve it in brackets here. Make that red. No, please. So then after that we can make it white again. So negative 9 times 10, which is 90. Negative 90. Negative. Yeah, there we go. So then I just add and subtract those together, and we can get here 20 x3 x to the power of 3 plus 80 x squared and 80 minus 45 is wait, what's that, 35? Right, yeah, 35x minus 90. And there we go. We can also do it with minus, and it's simple, just like just like adding. But however, here, let me show you an example. Erase this all. Okay, so we'll just make this a minus. So what happens here is we have g of x, so 4x squared plus 8x minus 9 minus 5x plus 10. However, when you subtract them with each other, the minus goes here and goes there too. So it becomes 4x squared plus 8x, right, minus 9 minus 5x, and the minus travels and then goes to minus 10, and then you just solve them as it is. So this and this, so you get make that this color, 4x squared, make that a different color, and 8 minus 3 is positive 3x, and then make that a different color, negative 19. And so that's it for our second big project. This is all we learned. So for our third big project, we learned how to do long division and learned about the remainder theorem. We learned about what the remainder theorem was all about and how we can use it to bypass doing the long division. So let's get started with long division. So for example here, we have a linear function, like for example x plus 5, right? And using x plus 5, wait, let me change this. We want to find out whether we can divide this one. So x squared plus 25x minus like 10. Okay, let's do that. Right? So let's make this equals to f of x, and let's make this equals to g of x. Okay, now then what we can do here is, using normal division that we know about, right? You know how to divide numbers. You can just put there x plus 5, and then we can just put a divide and put there x squared plus 25x minus 10. Now then, using what we know in division, we can just easily solve this. So how many x's can fit in x squared? 1x, so we can just put an x there, right? And then what we will get here, let me change this, x squared, and then you times x with 5, so plus 5x, right? Then you minus this, this one turns into minus, this one turns into minus. 25 minus 5x is 20x. Okay, so using 20x, you can pull down that negative 10, and then using that, we have to solve this. So let's turn this back to white. Have this become plus 20 times this, so 20x, yes, because plus 20 times 5, which is 100, and so minus, this one turns that minus, this one turns into minus, and so my negative 10 minus 100 is negative 110, and that is our remainder. Now then, we can write this like this. So what we have here is the divisor, right? Divisor, and multiply it with the quotient, right? So we have here x plus 5 multiplied with x plus 10, right? And then we add it, so let me move this a bit, and then we add minus it with the remainder. So 110. And this is our answer from our long division. Yes, as you can see here, the answer. So this is basically this is the basics to long division. Now moving on, how about the remainder theorem? How can we use the remainder theorem? So for example here, we have a question. Let me move this back up. We have a question that's asking us whether x plus 5 is a factor of x squared plus 25x minus 10. So if is f of x a factor of g of x? Now we could just do the long division like we did and easily solve for that. Or no, not easily, maybe a bit harder, but there is an easy way to solve it. So using the remainder theorem, we can just take the remainder, we can just take the number that we want to divide with the divisor and put it as x. So for example here, we have f of x is x equals x plus 5. We want to know whether this can go into this without getting without getting a number. That's how we basically explain it. So what we can do is we can change x to make this 0. So turn this into 0. This will become x is equals to negative 5. Now using that negative 5, we can put it into x here in the formula of g of x. So we can take g of, where is this, right? Negative 5, turn it back, right, is equals to, and then we turn all the x's into negative 5. So we have here, let me make this nice color. So negative 5, oh wait, I turned it already. Right now. Sorry, let me erase that real quick. There you go. Okay, so we have here negative 5 to the power of 2, right? Plus 25 times negative, just a dot, negative 5 minus 10. Now, as the remainder theorem states, if this is all of this is equals to 0, that means that f of x is a factor of g of x. So let's solve this. So we have here, let me turn this to a different color, negative 5 squared, so that's 25, right? And then we have here 25 times negative 5, which is negative 125 minus 10. So then from that we got negative 100 minus 10, negative 110. Now since this is not equals to 0, then f of x, let me just turn this back to pi, f of x is not a factor. It's not, so it's not a factor of g of x. Okay, so yeah, this is the basics of the remainder theorem. Let me make an example here so that it actually is a factor, so that I can show you step by step how we can easily find that. So then wait, let me change this. Wait, pause. Okay, let's start again from two equations. We have here f of x, right? and we have here g of x. This is just an example so that you will understand how we know it's a factor. So using this, right, we want to know if f of x is a factor of g of x. So that means we have to find the zero of f of x, find the zero of f of x, which is -2, because x plus 2 is equals to sorry, x plus 2 makes x equals to -2. So the zero of the zero of the of f of x is going to be -2. Now we're going to put -2 into g of x, right? So let's have your color blue. So we have -2 squared, right, plus, make that red again, 7 times, make that blue again, times -2 brackets, and then make that red, plus 10, right? So then we can solve this, and if it's equals to 0, that means x plus 2 is a factor of x squared plus 7x plus 10x. So we solve this, and we have here, let me turn this off to white so that it looks nice, 4 plus, sorry, not plus, negative, 4 minus 14 plus 10. And if we solve it, for minus 14 is -10, -10 plus 10 is 0. This shows that x of 2, x of 2 is indeed a factor of g of x. So that was just a little example to show you what happens, to how to find out whether it actually is a factor. So yeah, this concludes our big project 3. Okay, let's get started with our fourth big project, which is all about the binomial theorem. So the binomial theorem is an easy way to find out the answers to hard equations, just like this. So x plus y, for example, like 6. This would mean that you have to multiply them 6 times, right? So x plus y and x plus y. I shouldn't have done this too much. And x plus y, and so on, right? And you would multiply this, you would multiply this, then this, and then this, and then you get the answer, and then you multiply all of that with that, and so on and so forth 6 times, which is gonna take a really long time. So the binomial theorem helps you bypass all of that. So let's do an easy number. For example, we have 4. Okay, so this may look a little bit scary in the beginning because the equation is a bit hard. So for example, here we have x plus y to the power of n, because n could be any number, right? So what we have here, the binomial theorem says here that x plus y to the power of n can be shown by doing this. The sum of n, as you can see n here, from k equals 0, I'll get to that later, multiplied with n choose k, I'll get to that later also, times x n minus k and then y, which is n. So basically n here is the number that we have in the beginning, and k is basically 0 that goes on till n, and n choose k is it's about factorials, which I'll get to that later also. And we have here x to the power of n minus k and y n. So let me show you an example using an easy one. Let's make this 3. So we have here the equation. So let's start from k equals 0. So what we have here is equals to n choose k. So n right now is 3. So we have here 3, and since it's the first one, that means k is equals to 0, right? And then we have that multiply with x because we have x over there, n minus k. So n minus k, n is 3 minus 0, and y is n, which is 3. Oh wait, k, it should be k, sorry, this is k. Whoops, this is k. Wrote the equation wrong. So this is 0, right? So then we can just do this sum, so that means we add them together. So this is 3 choose 1, because k is 1, x 3 minus 1, and y, which is 1, because k is 1. And then we have, okay, this will be long. 3 choose 2, brackets. Oh, I should have color coded this. This looks ugly. So we have here x 3 minus 2, and y is equals to 2. And then moving on, we have plus choose 3, and then x 3 minus 3, and then y is equals to 3. Yes, I was confused for a moment there. Let me zoom out. Oh wait, no, wait, how do you zoom out? Options, zoom out. There, okay, there we go, better. So then there we have the full equation. Now first, let's start by solving the chooses. Now choose is basically 3 factorial, so let's start with this one. So let's solve this. So 3 factorial, which is basically 3 times 2 times 1, right? So 3 times 2 times 1, right? Over 0, which is 0 factorial, 1 factorial, 0 factorial, times with, okay, sorry, got a little confused there. So 0 factorial, and it's gonna be 3 choose n choose k is basically n factorial over n k factorial times n minus k factorial. So basically, let me explain this clearer so that you all understand. N choose k, right, is equals, oh sorry, there's no, I'm retarded. Fix that. N choose k is basically n factorial, alright, so what we have here is 3, that's why I put 3 there, n factorial over k factorial times n minus k factorial. So let's just solve this. So k factorial is 0 because it's 0 here, right? So so 0 factorial there, times n, which is 3, minus k, which is minus 0 factorial. Now if we simplify this, it's going to be 3 times 2 times 1, which is 6, right, over 1 times 3 times 2 times 1, 6, which is equals to 1. So the first part of our problem here is going to be 1. Now we can just erase all of this. No, wait, no need to. And so x to the power of 3, continuing on, y 0, which is practically 1, so we can just get rid of that. And yeah, so the first term of our answer to x plus y to the power of 3 is going to be x to the power of 3. Okay, so this is the beginning of our equation. This is all cancelled because this is all 1, right? So let's continue on. Plus, so we're continuing on over here. This is going to be 3 factorial, right? So let me solve this under. So 3 factorial, right, over 1 factorial, because k is 1, times 3 minus 1 factorial. Now if we solve this, we have here 3 times 2 times 1, 3 times 2 times 1 over 1. So let's just make that bracket. So 3 minus 1 factorial, which is 2 factorial, 2 times 1. Just cross these out, and then we have 3. So our next term is going to start with 3. So we have here 3. That's the answer of 3. Choose 1. And then we can just go on with this. X 2, y 1. So yeah. Now if we just continue it on, it's going to let's start again with the next term. So 3, choose 2. So 3 times 2 times 1, because 3 factorial, over 2 times 1, which is 2 factorial, times 3 so 3 minus 2, which is going to be there 1. So the answer of this one is going to be 3 times 2 times 1 over 2. So just cross 10 out, and we got 3, right? So what we have here is 3x y squared, and then 3 choose 3 is basically answering it. It's going to be 1. So our answer in the end is going to be y3. So this is the full equation from what we got from the remainder theorem. Okay, that seems simple enough. Now then, another thing that we learned was the what is it called? Okay, another thing that we learned was the Pascal's triangle, which means that we can literally bypass the binomial theorem and just do the Pascal's triangle. So the Pascal's triangle is basically like it's a triangle, as the name says. So for example, if we have here 1, right, this is 1, and we split it up to become 1, 1, and then we split those up to be 1, 2, 1, because there's only one way to get from here to there, but there are 2 ways you can get from here to there. Okay? As you can see, right, there's 2 ways you can get from here to there. 2. right? And continuing on, we have here, because there's no more space, so 1, this is 3, this is 3, and this is 1, right? So if we just keep continuing on, then we can get to a lot of numbers. And what if I told you that these are the first part of the equation? So for example, this is just one term, right, to the power of 1. This is 2 terms to the power of 2. This is, sorry, I got this wrong. This is power of 0, sorry. This is power of 1, linear, right? Linear has 2 terms. And this is quadratic, 3 terms. So this is to the power of 2. And this is what we got here, 1, 3, 3, 1. As you can see here, 1, 3, 3, 1. So this is to the power of 3. And if we kept continuing on, we can just easily find out the first part of the every single formula. So for example, if we wanted to find x plus y to the power of 4, right? We just go one step further. So 1, 3, 3, 1. Triangles. We got here 1, 4, right? And then 6, 4, 1. Now these would become the first part of the equation. Let me erase all of this because we don't really need it right now. Okay. Now using what we know, right? 1, 4, 6, 4, 1, right? So that's x plus y to the power of 4. Using these numbers, we can start to solve it. So 1, put a big space, 4, 6, 4, 1. Now since we have x, we can just put it to the power of n. So x to the power of n, which is 4, right? And y to the power of k, which is 0 right now because we're at the first part. 0, 1, 2, 3, 4. Plus. Just add pluses. And what we can do here is x to the power of 3, bring it down 1. 4, 3, 2, 1, 0. 4, 3. How about y? Y is going to be 1 because it's y to the power of 0, and then it's going to turn to y to the power of 1, and then it's going to turn to x to the power of 2 because it goes down 1. 4, 3, 2, 1. And y to the power of 2, x, and then y to the power of 3, and then y to the power of 4. As you can see, the Pascal triangle just easily bypasses the the binomial theorem just by doing these easy steps. So this is the thing that we learned from our big project 4. So I skipped big project 5 because it was almost exactly the same as big project 3. It's basically just the remainder theorem and a different way to write it. So moving on, let's start with the big project 6. So the big project 6 was all about imaginary numbers. Now imaginary numbers can stand for I, right? So we have here I. Let me zoom in, and move this up a bit. Sorry, there you go. I. Now I can mean I is basically root of -1. Now, yeah, it's an imaginary number because you can't square a number to get a negative number, right? So what mathematicians do is change it and turn it into I. Now, how can this be used in a quadratic formula, for example? So for example, we have here x squared minus any number, so 9x plus 1. Okay, now let me just, whoa, this is too big. Let me just erase this. Now then, what if we wanted to find out where it would intersect on the graph? So for example, this is the graph, right? There are 3 types of parabolas. Parabolas. The first one will touch the x-axis 2 times, as you can see here. 1, 2. The second type will only touch it once. Yeah, only one time over here. And the third type, let me just add a little bit more, will go above and never touch it, right? So what if we wanted to find out whether the graph was touching the x-axis twice, once, or none at all? That's when imaginary numbers come into practice. And that's when we learn about discriminants. So basically, from the quadratic formula, as you can see here, the quadratic formula is equals to negative b plus minus, remember this already, negative b squared, sorry, not negative, okay, I don't really, ouch, make it bigger, make it bigger, okay, sorry, b squared minus 4ac over 2a. See, I remember it. Now then, the discriminant is basically this. Now using the discriminant, right, b squared minus 4ac, we can find out whether it is touching it twice, once, or not at all. So what we do here, if this is equals to 0, let's start with that. If it's equals to 0, that means it touches it once. Now if it's less than 0, or an imaginary number, right, it will never touch the x-axis. So less than 0. If it's greater than 0, that means it will touch it twice. Okay, so yeah, let's just solve this. So if we put our equation into discriminant, then we can get here, negative 9 squared, right? So negative 9 squared, because negative 9 is b to the power of 2 minus 4ac, so 4 times 1, right, times it with 1. Now if we see here, this is 81 minus 4, which is a positive number. That means it touches it twice. Right, it's 81 minus 4. 77, right? Yeah, 77. Okay, so then how does imaginary numbers go into all of this? Let me find an equation that doesn't touch the line. So what if it didn't touch the line? Wait, so let's turn this all and change the equation to make so here. okay, so moving on, we have here a equation that's going to be imaginary numbers. So first we have to turn it into standard form. So 6 x squared minus 2x plus 3. Now if we do the thing that we did with the discriminant earlier, and we put it into the equation, it's going to be 4 minus 4 times 6, which is 24. 24 times 3, which is 72. 24 times 3, 72, I think. Right? And it's going to be a negative number. Yeah, negative 68. Okay. Now, if it's negative, that means when we solve the quadratic formula, right, if we put all of these into the quadratic formula, there's gonna be a root with a negative number inside it. So instead of talking, let's just do it. So we have here x is equals to 2 plus minus root of negative 68. We already got that from discriminant. Negative 68 over 2 times 8. 2 times 8 is 12. Okay. Now when we solve this, it's gonna be, wait, what's 68? Root 68. 68. So 2 plus or minus. Okay, let's just make it root negative 68 I. There we go. Imaginary number placed. So that's how imaginary numbers are used. And that's what we learned from our big project 6. Thank you.